Let's now take a look at the idea of a p-series. A p-series has the form, the sum n equals 1 to infinity of 1 over n to the p. So I get 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p and so forth, where p is a positive constant. Now, the convergence for a p-series. The p-series will in fact converge if p is greater than 1. Otherwise, it's going to diverge if p is less than or equal to 1. Now, actually, in a later exercise, and I believe an example that I've done or will do, we actually talk about proving this. We go through some steps to show how this is realistic. Now, the harmonic series, I want to show that the harmonic series is actually divergent. The harmonic series is the sum n equals 1 to infinity of 1 over n. So in this case, this is a p-series where p happens to be equal to 1. So how do we show that the harmonic series is divergent? Well, let's use the integral test. So I'm going to let f of x equal 1 over x, which is x to the negative 1. That implies that f prime of x is equal to negative x to the negative 2, which is a negative 1 over x squared, which is less than 0 for all x in our domain, because remember we're starting at 1 and going to infinity, so x equals 0 is not in our domain. So when I say for all x, I'm really making reference to the fact that it's in our domain. All right, so I can integrate this. So I need to take a look at the limit as b goes to infinity of the integral from 1 to b of 1 over x dx, which is equal to the limit as b goes to infinity of ln x evaluated from 1 to b, which is equal to the limit as b goes to infinity of ln b minus ln of 1. Well, this goes to infinity, so this is infinity minus 0. So obviously that's infinite. Therefore, the integral is divergent. It goes to infinity. Therefore, I can say that the series n equals 1 to infinity of 1 over n is divergent by the integral test. We'll take a look later at other forms of the p-series, and we'll actually use the p-series quite a bit.